Today we'll see what is a denial of service attack, and we'll see how you can prevent this attack from happening by using the pull over push pattern in Solidity. To start off, we have this auction contract that should facilitate an auction like you would have an auction in real life, but this auction is of course on the blockchain, and it simply has a bid function that is payable and can receive Ether. And this function basically allows you to bid, and it checks that you've sent the highest bid. So it checks if the Ether value you've sent is greater than the current highest bid. If so, we'll refund the current leader. So we'll refund the amount they've sent. We want to make sure that this transfer is successful, and after this is done, we'll just set the current leader to this person and set the highest bid to this Ether value. So if I deploy this auction contract now and try to send money from let's say this address, I'll just send 1 Ether. So if I click on bid, the highest bid will be 1 Ether, and this address, my address, will be the current leader. If someone else comes in that wants to deposit 2 Ether, he'll send the money, he'll call this bid function. Now we'll refund the other person 1 Ether, basically the amount they've sent. The highest bid will be 2 Ether, and it will change to my address. And in the contract balance, we'll have 2 Ether. So on the surface, everything looks fine. But the problem occurs in this line when we try to refund the current leader their amount. Only if this current leader is a contract that cannot receive Ether. So let's first clarify that this function can be called by a contract itself. So this current leader can also be a contract instead of an externally owned account. So if we have an attacker contract like so if a leader can be a contract, this contract should be able to receive Ether for this transfer to be successful and to continue on executing. And I probably should have mentioned, but denial of service attack is basically when you prevent a function to be called basically by reverting anytime anyone calls this function. And that's what we're going to do to this bid function using this contract. There are 2 ways a contract can receive Ether. So first, you can send a Ether into a function labeled as payable, like we have here with the bid function, or you can send Ether directly to the contract itself if the contract has this receive or fallback function. And intentionally, I'm going to make so this attacker contract does not have any way of receiving Ether. And let's see what happens now if I deploy the auction and try to attack this contract. So in the attacker contract, simply we have an instance of this auction contract, and for us to create this instance, we have to pass in the address of the auction contract itself. That's why I'm deploying the auction contract first. So if you select attacker, you're going to have to paste the auction contract before you deploy the attacker contract. So now we have the attacker deployed. Let's try this one more time. Let's use this address, and let's say he wants to bet 19 Ether. So he clicks on bid. Now the current leader is 19, and we have this address as the current leader. So this is fine. Now he has 8 Ether. Let's say this other person comes in. This is the attacker, and he wants to perform a denial of service. So what he has to do is send some value greater than 19 Ether, greater than the highest bid, let's say 29 Ether. So he has already deployed their attacker contract. So he'll just call the attack function on this attacker contract that just simply bids this amount of Ether, basically the Ether we've sent into this contract. And now the highest bid will be 29 Ether, and the leader, the current leader, will be this address of the contract, not the person who called this function, the attacker, basically the attacker's EOA account. So what happens now if a third person comes in? He sees that the highest bid is 29, and wants to deposit 39 Ether. So he simply clicks on bid and the transaction fails. So even if, let's say, another person will try this with another person, he will even deposit, is willing to deposit 80 Ether. So he clicks on bid and the transaction fails again. And this is because we are trying to send money to the current leader whenever someone tries to bid. The current leader is the contract that cannot receive Ether, and this is because this message call will fail every time. So we've basically made this bid function unusable because it will revert every time you try to call it. And this happens because we are trying to push funds, push Ether to the contract address instead of allowing them to pull this money. And we'll see how to use the pull over push pattern in this auction v2 contract that is updated and not vulnerable to this denial of service attack. How can we solve this in this auction v2 contract? So in the bid function, now you can see the main difference is instead of pushing Ether to the sender, to the current leader, all we're doing is we have a balances mapping where we track for each address, for each current leader that goes through this auction, we track the amount they can withdraw. So we just track, we don't push, we don't make any external calls. But we've added an entirely new function called withdraw, where anyone can come in, but of course this will only work for the people eligible to withdraw, to refund some money. So now every leader can come in and withdraw their money, and we know this how much they can withdraw because we are just tracking instead of pushing here in the bid function. So they'll come in. If they're not the current leader, we'll just take their balance, set it to 0, and try to send their money. And this way we're still sort of pushing the funds. As you can see, we're sending them funds again, but this is isolated in a function itself. Someone cannot perform now a denial of service attack. So now I'm going to deploy the auction v2 contract, and we'll see how an attacker cannot perform a denial of service attack. Let's say I'll use this address as an example. Let's say he wants to deposit 19 Ether, he'll bid. Now the highest bid is 19 Ether. He has 80 Ether. Now the attacker comes in, he deposits 29 Ether, and or he tries to attack this by calling attack on his contract. Now the highest bid is 29 Ether. And notice here, the previous current leader did not get their money back because we're not pushing funds to them, but we're allowing them to pull their money. And if we check the balance, we can see this person is eligible to receive 19 Ether. So if he just calls withdraw, transaction will succeed and he'll get their money back. So now if we check the current leader, we saw this functionality works, the refund system. We'll see now that the current leader is this address, the contract address. And what we can do is, let's say if someone comes in, a new person, and wants to deposit Ether. Let's see if the attacker succeeded in this denial of service attack. So if he calls bid, we can see the highest bid is updated to 48 Ether. And now the current leader is this address. And our contract is eligible to withdraw their money. The contract that tried to but didn't succeed to perform a denial of service attack.